Okay, so I want to do a couple of examples. So here's example 1. Suppose I want to find the limit of the sequence an equals the n plus first root, there's an n plus 1 here, of n divided by n minus 1 to the power n squared minus n. Let's write this a bit more clearly. So what's the limit? What? Don't you just see it? Okay, so do you agree that there are too many n's here? 1, 2, 3, 4, 5 n's. This is not something you can just look at and see what the limit is, okay? But you should be able to have preliminary intuition that E is somehow going to be involved, okay? And let me show you why. So don't be scared. I'm going to rewrite this, and it's gradually going to take the form of something that goes to E, or some variation of E. Okay, so do you agree that I can rewrite this as n divided by n minus 1 to the power n squared minus n divided by n plus 1? Do you agree that this is the same thing? Okay. Now what I'm going to do is I'm going to subtract 1 and add 1 over here. And the reason for doing that, let me do it in blue, is precisely to make it E-ish. E-ish. So I get this, and on the power I'm going to write it n times n minus 1 divided by n plus 1. Does everybody agree to this highly non-trivial step? Yep? Okay. Now this equals 1, that's this, plus 1 over n minus 1. That's the stuff inside the parentheses. Do you see E starting to show up? Okay. And the power up there, well, I want to leave this n minus 1 here, because that's exactly what I have here. And then the rest, I'm going to write as n divided by n plus 1. Does everybody agree so far? Now, what would not be correct would be to say this goes to E, therefore I can rewrite this as E to the n over n plus 1. This is completely false. I'm going to erase it in a second. I'm already feeling uncomfortable just for having written it. Okay? Why? Because what we're doing so far is pure algebra. We didn't go to the limit yet, right? The arrow n goes to infinity did not show up yet. Do you agree? Right? So if I want to put that arrow, if I want to do this, this would at least make some sense, right? Because it's taking these n's to infinity and saying, okay, 1 plus 1 over a sequence that goes to infinity to the power a sequence that goes to infinity goes to E. But that would be taking some of the n's to infinity and leaving the others for later. Big no-no. Can't do that. Right? And the reason you can't do that, well, one reason you can't do that is that if you could do it, then the sequence 1 plus 1 over n to the power n, you could say, okay, 1 plus 1 over n goes to 1. 1 to the power n is always 1. The limit is 1. And the limit is not 1, it's E. All the elements are between 2 and 3, right? Okay? So never, never, ever take limits in steps. Okay? The n goes to infinity has to happen simultaneously for all n's. We said that, and we're saying it again. And I think here it's clear why it's wrong. Okay. So I'm going to leave this like this. And the statement about this, well, what I'm going to do is do a +1 -1 trick here, too, just so we see what's going on, and rewrite it now as 1 + 1 over n minus 1 to the power n minus 1. All of this to the power n plus 1 over n plus 1 is 1, minus 1 over n plus 1. Do you agree to this? And now I'm going to take all the n's simultaneously to infinity. What's inside here goes to e. That's the theorem we had. The power here goes to 1, because this goes to 0. So the limit is e to the power 1, which is in fact e. So it turned out that this is exactly e, not some...
How did you get e?
Well, the stuff in the parentheses is of the form 1 + 1 over a sequence to the power that sequence, where the sequence goes to infinity. Do you agree that that goes to e?
Yes.
And do you agree that the power here goes to 1?
Yeah.
So the limit is e to the power 1. Do you agree? Hmm? Okay. Another example, which is not related to e anymore, maybe I'll write it here. Another example, so example number 2. This example is not related to e, it's related to the theorem that we had, that any monotone bounded sequence converges. So suppose you have the sequence a1 equals 1/4 and an equals an minus 1 squared plus 1/4. What did we call this? Right, this is a recursive sequence. Okay? Remember, we had a few examples of those. And a very standard way of handling them is using that theorem. Okay? So, show, this is very, very easy. I'm going to leave it for you to complete the details. So show by easy induction, that, first of all, an is increasing. And second of all, that an is bounded. In fact, an is less than 1/2 for every n. Okay? The way to guess this 1/2 is, for example, well, the first element is 1/4, then the next element is squaring 1/4, which makes it smaller than 1/4 and adding 1/4. And then you keep squaring the elements, making them smaller and adding 1/4. So you can see that you're not going to exceed 1/2. That's just intuition. Prove it. Prove both these facts. Easy induction. Straightforward induction. Okay? So what's the conclusion? It converges. So by theorem, it's bounded, it's monotone, an converges. But this doesn't tell us what the limit is. It just tells us that it converges, right? The way to calculate the limit when you have a recursive formula is the following. If you know, I'm going to rewrite this formula on the next board. It's induction, and I'm calming you down by saying that it's easy. Okay, it's not that there's a theorem, easy induction and hard induction. It's just induction, but it's a very easy application of it. Okay, very easy. Okay, so how do we calculate the limit? So calculating the limit. So we take the recursive formula, which was an equals an minus 1 squared plus 1/4. And look at what we know. We already know that the sequence converges. So when n goes to infinity, an goes to some L. Let's call the limit L. Right? What about an minus 1? We showed that it converges. That was the theorem. We showed that it's in. We didn't show. I said show. I gave you that as homework, and I'm absolutely positive. Yeah, I'm absolutely positive that you can do it easily. So I'm considering it done. Okay. So now you agree. Okay. So there's the limit L. Call it L. Do you agree that an goes to L? Well, that's the limit. What does an minus 1 go to? Also L. It's just a shift of the sequence by one element, right? The limit doesn't change. So this goes to, by limit arithmetics, to L squared plus 1/4. Do you agree? And if they're equal, these are going to be equal. So from the recursive formula, we learn that L equals L squared plus 1/4. Whatever the limit is, it's going to have to satisfy that. Okay? So what? L squared minus L plus 1/4 equals 0, right? Now it's just a quadratic equation. The variable is L rather than X, but we can handle that, right? Okay, so what we get is L equals 1/2. Okay? So again, you can fill in the details, use the quadratic formula, and you get that L equals 1/2. So that's how you find the limit. Good? Let's do one more example of this form. One more example. So, example 3. Suppose we have a recursive formula, a1 equals 3, an plus 1 equals 1 plus 2an. Okay? So let's do the same sort of thingy on this equation. So this goes to L, and this goes to 1 plus 2L, and therefore L equals 1 plus 2L. So subtracting L here and moving this, we get L equals -1. Do you agree? I can see some uneasiness in the audience. Something went wrong, right? Why did something go wrong? This is a positive, all the elements are positive, right? And moreover, they just get bigger and bigger and bigger. Do you agree? This is the sequence what? 3, the next element is 1 plus 6, 7, then 15, then what? 31. Do you agree?
Yes.
No way the limit is -1.
Doesn't converge.
It goes to infinity, clearly. Okay? So something went wrong, and what went wrong is this. And if that went wrong, everything else is completely wrong, big X. Okay? Nonsense. Nonsense. Okay? So the lesson, the take-home message from this example is, you cannot dive right away to using this trick to calculate the limit before you know that the limit exists. You're going to get nonsense. Okay? When the limit exists, the method we used in example 2 is perfectly okay. But you first have to show that the limit exists. And the standard tool for doing that is showing that the sequence is monotone and bounded. Clear? Yes?
Does the limit only exist if it's monotone and bounded?
No. No. That's what happened in this example. In different examples, completely different things example. You know that sequences don't have to be monotone in order to have limits. Right? Let me convince you of that, again, with no words. Right? Sequence can wiggle back and forth around the limit and gradually, right? Doesn't have to be monotone in order to have a limit. Okay? If it's monotone and bounded, it converges to its supremum or infimum, depending on the direction of monotonicity. Yes?
So what went wrong here is that there is no limit in the first.
Right, there is no limit, and therefore this is false, saying that they're equal is complete nonsense, and we got nonsense.
Is the limit infinity?
In this case, obviously, the limit is infinity. Okay? Okay, good. So our next topic is in fact what's called subsequences. Let's erase some working space here. So when you have a sequence, often it's for various reasons, you would want to look not at all the elements of the sequence, but just at some of them. Okay, and that's what's called a subsequence. So definition. Let AN be a sequence obtained from AN by deleting some of the elements is called a subsequence. Let's do examples. So example 1, let's look at the sequence. So this is going to be AN. AN is going to be 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, dot, dot, dot. This is AN. Is it bounded?
Yes.
Does it have a limit?
No.
No. Okay. Is it monotone?
No.
Okay. So do you see inside AN a subsequence 1, 1, 1, 1, 1, dot, dot, dot? Okay? How do you get that subsequence? You knock away all the zeros.
N plus 1.
Hmm?
It's like just every second n.
It's just all the odd indexed elements. Okay? So this is a subsequence of AN. Okay? Do you agree that this is a subsequence of AN? Do you agree that this is a subsequence of AN? It's like sub anything. It's a subsequence. Do you agree that this is a subsequence of AN? If you're wondering how I got it, well, I knocked away this one. I got left with this 0, then this 1, then this 0. Pew, go away. I got this 0, 1, go away, 1. In fact, any combination of zeros and ones is going to be a subsequence of this sequence. Do you see that?
But you don't have to follow an order of subtracting an element?
No. In general, in a sequence, nowhere did we say that there has to be a rule or a formula or any form of non-randomness. Okay? Well, there is a rule there, right? If you take the sequence of prime numbers, there's a rule. Just take the prime numbers. In general, a sequence is just an ordered infinite set of numbers. Okay? Clear? How do we denote subsequences? Okay. So here for AN, we have a formula. AN is 1 if n is odd, 0 if n is even. Do you agree? For this subsequence, we also have a formula. This is the sequence, the constant sequence 1. Right? Do you agree? But just saying that this is the constant sequence 1 is forgetting the fact that it's a subsequence of this. It's just saying, hey, I'm the constant sequence 1. You don't know who my parents were. Okay? And oftentimes we want to keep in mind where it came from. Okay? And the way to do that is confusing. So I'm going to write it. Maybe we'll do one more example, but don't worry, we're not gonna get lost in this subsequence notation business. Okay? So if this is AN, what do I want to say here? I don't want to just call it, we can call this BN, which is just 1. This would be true, but that's not remember that it's ANs. The way to remember that it's ANs would be to call it A, but I'm not taking all the n's, I'm only taking the odd ones. So I'm going to write it A 2k minus 1, where, let's use the full notation, where k goes from 1 to infinity. So here I'm saying, hey, I'm taking the ANs, but which ones? Well, when k equals 1, I'm taking A1. That's this element. When k equals 2, I'm taking A3. When k equals 3, I'm taking A5. Do you see that? Does everybody agree that when I run the k's from 1 to infinity, here I get exactly the odd indexed elements of AN? And this subsequence would be A2k. K goes from 1 to infinity. A2, A4, A6, A8, etc. Do you agree? Everybody? So that's the way we denote subsequences when we want to emphasize the fact that they're subsequences of... And this will not have a formula, of course, because I just took them randomly. Okay? Here's another example. Here's another example. So example number 2. Let's look at the sequence. So AN is going to be the sequence 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. That's AN. So AN is what? AN is just a sequence 1 over n. Do you agree? Suppose I want, as a subsequence of the ANs to take the sequence 1, 1/4, 1/9, 1/16. Wait, 1 second. Let me. So what would be the formula for this sequence in its own right? Right. This is the sequence 1 over n squared, Bn. Okay? But if I want to emphasize that it's a subsequence of the harmonic sequence, how do I do that? How do I denote it? A k squared, where k goes from 1 to infinity. Do you agree? The first element is going to be for k equals 1. You get a1. That's the 1 here. The second element, for k equals 2, you get a4. a4 is 1/4. And so on. Everybody good? Question? You seem confused.
Yeah, I'm trying to. How I will it?
Well, when we write a sequence, when we write an equals 1 over n, okay, how do we get the elements? We plug in n's. We plug in 1, we plug in 2, we plug in 3. So saying that this is the formula for this is saying you plug in 1, you get the first element. You plug in 2, you get the second element. You plug in 3, you get the third element, and so on. In this formula, if I plug, the index, the running index is k. But the elements are not just ak, they're ak squared. So if you plug in k's, running k's, plug in 1, you get what? You get a1. That's 1, because it's the ANs. If you plug in 2, you don't get a2. You get a4. That's the second element of the subsequence. Good? Everybody? Question? Yeah.
To get that expression for the subsequence, is there a method to get it or just looking at it?
Sometimes it's easy. If you see the formula for this, it's kind of evident. Sometimes you have to think and decipher what's going on, just like finding a formula for a sequence. Not if it's a subsequence of something. Okay, sometimes you have to be creative. Okay. Now a few theorems that go along with this topic. This is a bigger topic than what we're doing. We're really just touching the tip of the iceberg in this topic of subsequences. But it's enough for our needs in this course. Okay? So a theorem, if an has a limit, then any subsequence of an has the same limit, has that same limit. Including infinity and minus infinity. And this, I'm not going to write the proof, but let me say it. It should be very convincing. If your sequence, like this one, converges to 0, right? What does it mean in terms of the definition? That if you go far enough, everybody's going to be close to 0, right? That's convergence. Is everybody with me? Okay. So if you take a subsequence, if you take just part of the elements, throw away some of them, still if you're going to go far enough down the indices, you're going to end up in that epsilon neighborhood of the limit. And if you want a smaller epsilon, go further down the indices. Do you agree? So if it has a limit, any subsequence you take is going to have that same limit. If it doesn't have a limit, anything could happen. Previous example. Example 1. This does not, look at this board, this does not have a limit, right? And in fact, here's a subsequence that does have a limit and it's 1. Here's a subsequence that does have a limit, but it's 0, right? So there's the not having a limit doesn't indicate anything about the subsequences. Having a limit indicates that all the subsequences are going to have that same limit. Okay. So a corollary of this, do you know the word corollary? A consequence of this theorem is that if an has subsequences with different limits, if you take a sequence, like in example 1, and you find two subsequences that have different limits, like, who talks like that? Do you know who talks like that? What's his name? Gollum, from the Lord of the Rings. Filthy hobbitses. Yeah. So if you have a subsequence, that's why I said it was subsequences. Okay. So if you have two subsequences with different limits, what does it indicate about the original sequence? Right, it diverges. Because if it had a limit, all the subsequences would be the same. So if an has subsequences with different limits, then an diverges. Clear? Okay. Now, definition, a limit of a subsequence is called, do you know? Right. A limit of a subsequence is called a partial limit or a sublimit. A partial limit of the original sequence. Okay, so a limit of a subsequence is called a partial limit of the original sequence. And I just want to do one example to give you some flavor, okay, of how intriguing this topic can be. Okay, but we're really not going to do it. We're not going to spend a lot of time on this. So, example, can you find a sequence such that every natural number, every n, is a partial limit? Suggestions. The examples we had so far, in example 1, there were exactly two partial limits, 0 and 1. In example 2, well, example 2 had a limit, so all subsequences went to 0, so there was just one partial limit. an. So an equals n. Here's our first candidate. This sequence has a limit. It goes to infinity, right? Any subsequence you're going to take is going to go to infinity.
Does the subsequence have to go to infinity?
Show me a subsequence that doesn't go to infinity.
A of 1.
A of 1, just this element, is not a subsequence. In the original definition of a sequence has infinitely many elements. Okay? So a subsequence, by definition, is a sequence obtained from the original sequence by throwing elements. If you throw all of them and are left with only one element, that's not a sequence. Okay? A sequence is always infinite, by the definition that we gave.
You're asking for a sequence with a formula?
I don't need a formula. Just tell me what to write.
1 to infinity, infinity times.
So you want to do this, and then after you get to infinity, start at 1 again. Well, there's a problem here. What's the index of this element going to be? Is it going to be A17? Bigger, A95? Almost. Do you agree that there's a problem here? This is not indexed by the natural numbers. This is not a sequence. You can't go to infinity and then you never get there. But you're getting there. You're getting there.
Well, you could ridiculously just do some sequence where you say like, for example, every n which is divisible by a certain number, you can define it for being 1, for example.
Okay. So do you agree you want to have, for example, infinitely many 1s there? And that will give you the subsequence going to 1. But you also want infinitely many 2s. And infinitely many 3s.
Yeah, since we have infinitely many prime numbers,
Okay.
we could like define for every n which is divisible by a certain prime number, we could define a number line like 1, 2, 3, 4, 5.
Okay. Suggestion?
Digits of pi.
Ooh, no. Digits of pi, all the elements are between 0 and 9. Right?
No, we could take like.
Where are you going to have in the digits of pi a subsequence with limit 25? Here's the answer. Here's the first element, 1. Here's the second element, 1, and then 2. These are the first 3 elements. No. Then 1, 2, 3. Then 1, then 2, then 3, then 4. Then 1, then 2, then 3, then 4, then 5. Then 1, then 2, then 3, then 4, then 5, then 6. Then 1, ... Do you see a subsequence here? I didn't give a formula, but I think what I did is clear, right? You can go on. Do you see a subsequence whose limit is 1? Just take all the 1s. How many 1s are there? Infinitely many. That's a subsequence whose limit is 1. Do you see a sublimit whose limit is 17? Do you see it? Does everybody see it? Right? There's going to be the first 17 is going to show up somewhere out here. You don't have to follow me with the camera. There's going to be a 17 somewhere out there. And then there's going to be a... Once the 17 appeared, it's going to appear again and again and again and again. Do you see that? So do you agree that this is a sequence? It's well defined, even though I didn't give a precise formula for it, such that every natural number is a partial limit. Good? Okay. Here's a ultra challenge, and I'm going to mark this with an asterisk, and please only do this if you can't fall asleep, or if you already know everything else and feel completely like a master of standard calculus, then try this. Find a sequence such that every x in R is a partial limit. This is really a just to challenge you guys. Don't try it if it scares you, and I'm not going to say the answer because it takes explaining. Okay? And I don't have time to do it. I want to state later. I want to go on. So I want to write what I want to write now is a very, very important theorem about subsequences. And it's the following. So theorem and the theorem is named after two mathematicians, and that's how it's usually called. So it's called Bolzano-Weierstrass. I think there's another E here, but I'm not sure. I hope I'm not misspelling this. I think that's the way you spell it. Okay, Bolzano-Weierstrass. And the statement is the following. Every bounded sequence has a converging subsequence. I'm not going to prove this. The proof of this I think this would be the first non-trivial theorem in this course. Non-trivial in the sense that it's not just putting together previous theorems and definitions in sophisticated ways. This takes an idea, okay? This is not something you can try on your own, usually. Maybe there are some bright people here that can, but it's not a standard exercise in this course. I want to just convince you that it's not a trivial statement. The only assumption on the sequence is that it's bounded. So here's A, here's B. The only assumption on the sequence is that all the elements live between A and B. A1, A2, A3, A4, A5, A6, A7, A8. You don't know anything else, just that they're bounded. Okay, that's a very light assumption. That's not saying much. Do you agree? And the claim is that somewhere in there, in that interval, you can put your hand on a subsequence that converges. Not all the elements, but there's going to be a subsequence, and we know what subsequences are, in between those completely, oddly behaving elements that have no rule to them. They're just, somewhere there's going to be a subsequence converging. Okay? And that's it. There's no additional data. That's all you have to work with a bounded sequence. How do you tackle something like this? Okay, so this is not a trivial statement, but it's true. Okay, but it's true, and it's very, very important and useful in theorems to come. Okay, suddenly, even when there's apparently no sequences involved in theorems about functions or integrals, suddenly there's going to be a statement by Bolzano-Weierstrass, blah, 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 blah. Okay, so that's this statement, and we still have a bit more stuff to say about sequences, and the key thing we want to say about sequences, and we'll do that next time, is relating sequences back to functions. Okay? Please, for next time, go over the stuff we discussed about functions, because next time it's back to functions, back to limits of functions, and starting new topics such as continuity. So thank you.